till we are joined by your colleagues. Let's see if you have questions. Your quiz, inshallah, the grades will be announced over the weekend, maybe by Friday. Inshallah, you will find them there. I'm done with section 2. Your section is almost done, so inshallah Friday you will get that. After the class, there is a couple of announcements that will appear on your Blackboard system. One of them is for quiz number 3, our last quiz, in about a couple of weeks. So the dates as well as the material is there for the quiz. You will also see another announcement for full 8 points of bonus point activities. So I'm giving everyone chances for 2 activities. One of them will be a bonus quiz in the last week, week 15, on the topics that we cover in chapter 8, the one that we are doing right now, the design chapter. And the sections that are relevant are mentioned there in the announcement as well. That's a totally bonus quiz. So in addition to the 15 points we have for the other 3, this will be extra 5 points for the grab. Of course, if you don't want them, don't attend the quiz, don't answer. But if you want them, this is like an extra for everyone. That should make it for anyone who was missing of one of the quizzes, wants to improve his grades. So that would be a good chance. The other activity, which was 3 points, also 3 full bonus points out of the 100, is to type or provide a typed 2-page maximum summary of the design of any jet aircraft, not propeller aircraft, jet aircraft. So you pick anyone, 787, Dreamliner, Tornado, whatever, pick any jet aircraft and provide a 2-page summary of its design. Of course, you will do some research on the design considerations over the internet. What was the driving factor for design? Was it the short takeoff distance? What was important about this design? Was it the higher speed, the larger capacity, and how did this affect the design of the aircraft? So, for example, the use of or the need for higher internal volume required that we have like an oval fuselage, not circular fuselage, maybe. Okay, whatever. So what was the major design requirement and how did it affect the design? No more than 2 pages. 1 page is fine, but I'm putting a limit because students, when you tell them do research, they just go and cut and paste pages and pages from the internet. So no more than 2 in your own language. Okay, and that's the due date for this is also week 15. So you still have a lot of time to work on this. And you will learn how these requirements affect the design as we go in our lectures of chapter 8. Okay, so you should see this in your system today, inshallah. Any questions, concerns?
Only jet aircraft, right?
Yes, only jet, not propeller, jet aircraft. And the reason for, and let me give you a hint on, not a hint on this. What do I mean by the requirements driving the design? If you look at chapter 9 of your textbook, it deals with the design of jet aircraft. You won't find many equations there. It's just telling you very few differences between jet and propeller, but there are case studies in this chapter. So what I expect to see from you is something like one of these case studies, but smaller. Please don't pick anyone from chapter 9. Pick any other aircraft. So in these sections, it's picking, I think, the F-22 aircraft, as well as the Boeing's maybe 707, if I remember correctly. That's a very old transport aircraft. And from there, the 727, the Boeing 727. And he mentioned how the requirements affected the need. Now, it was done in details in the textbook. Okay, because it's a textbook, it wants to explain so many things. I want you to do something similar, but on a smaller scale in no more than 2 pages. Okay. You don't have to follow the same order that's presenting in chapter 9, but it can give you a guide on what we are expecting to see. Okay. Any jet aircraft. Okay. Any questions? So can someone remind us what did we do last time?
معلش يا دكتور ممكن بس اسال سؤال على ال 3 point bonus.
Yes.
هو يعني الموضوع عن requirements of design ليش صمموه بالطريقه هذه ولا؟
بالضبط. Let me give you an example. Let's talk about the design of the Dreamliner 787, for example. By the way, it doesn't have to be a new aircraft. It could be an old aircraft because design is the same. 787, the main driving factor for, I will go and do research. Why did they develop the 787? What was the design driving factor? And you will find that it was efficiency, fuel consumption, and weights. Accordingly, the weight, of course, in order to have better efficiency and lower operational costs. This is the driving factor. So as I continue my research, I will read this. I will read that the objective was to produce a more efficient aircraft. So what they did is that they decided to reduce the weight by using a full composite fuselage. So that was the main decision that was affected by the requirements. Also, they designed a whole new wing, completely different from the wings that were there before, with these bent tips at the ends, and that improved the aerodynamics, reducing the fuel consumption. Okay. Also, they used a new type of engine that has a lower value of C. So all of this, I'm not gonna come up with. I'm not just gonna guess. In my research, I will see these pieces of information and I will collect them and I am gonna put it in my report. Okay, so you need to introduce us to the aircraft, and in your work you must show the requirement as well as the effect on the design. I'm not saying these are the only 2 parts in what you write, but these are the critical parts that have to be there. Does this answer the question? Okay.
Yes.
Okay. So can anyone remind us what did we do last time? We were designing a propeller aircraft, and let me, here we had the requirements, some requirements for the propeller aircraft. It was carrying 5 passengers and it was going through a maximum range, ceiling.
Doctor.
Yes.
Are you sharing the screen with us?
I hope I am.
No, we can see.
Okay, let me share it. Thank you. Let me see why it's not sharing. Okay. Do you see it now?
Yes, it's fine.
Okay. So we had a design of a 5-passenger aircraft. What parts of the design we covered last time?
Weight estimation.
Yes, weight estimate. What is the order of the weight estimate in our 7 points of thinking in the design process? Is it the first point, the second, the third? Weight estimation is?
I think it's the second.
It's the second, right after the requirements. So we started with the requirements, studied the requirements, went and calculated the weight estimation, and today, inshallah, we're gonna go through the third step, which is calculation of some critical performance parameters. Knowing only the weight and the requirements, find me CLmax of this aircraft, maximum lift to drag, wing loading, and thrust weight ratio. So we will pick whatever requirements are relevant for each one of these, and we are going to find them. Okay, so that's the main objective, because if I have these parameters calculated, I will gain a lot of information about the aircraft. I can divide the weight by W over S to get the wing area. I can divide the weight by T over W to get the thrust. Sorry, T over W divided by the weight to get the thrust. And that will tell me a lot about the aircraft. I will be able to start drawing the aircraft at that time. So today we are going to start with the CLmax as well as the wing loading, and next time we are going to do the thrust weight ratio and then the lift to drag ratio. Okay. So here are the requirements, and we're going to say how would these requirements drive the design. Which of these requirements is affected, that's a wrong question. Which of these requirements is directly related to CLmax? If I go into the equation of maximum speed, will I find CLmax? If I go back to chapter 5, will I find CLmax? No. If I go to the range, I don't have CLmax. Ceiling, no. There are other parameters, but CLmax is not there. Rate of climb, nope. Stalling speed, yes. That's the requirement that will give me the CLmax. Okay. But the problem with the stalling speed is that in order to get CLmax, I need the wing area. Stall speed, wing area, I can get CLmax, just like any of the problems that you have been solving throughout the year. So I cannot use this one. So unfortunately, there is not a good starting point from the requirements here that will help me to get CLmax. Maybe it's the type of the aircraft that might help me then. So we will start by looking at this type of aircraft. This is an aircraft that's carrying 5 passengers plus a pilot equals 6. Why don't we look at similar aircraft and see if we can get CLmax from their designs? So my team would do some quick search on similar aircraft. So here are 4 similar aircraft that carry 5 passengers. Now in your design project, you have different requirements. You have different aircraft. It's an aerobatic aircraft. So your team can do some search on these aerobatic aircrafts. Now, when I say search, doesn't mean I will go into the internet, type the name of the aircraft and get everything that's posted about it. That's not a good way. What do you want to do? I want to get CLmax, so I will be interested in the airfoils of these aircraft. So for our example that we are having, we have one aircraft, Beechcraft Bonanza, would have this airfoil in the root and this airfoil at the tip. The Paron would have this airfoil at the root and this one at the tip, and so on for the other aircraft. I'm doing this to gain some experience. What type of airfoils are being used in this category of aircraft? So the first thing you realize that all of them will have different airfoils from the roots than the tip section. And the difference between the 2 airfoils is basically in the last 2 digits. That means it's in the thickness ratio of that airfoil. So all of these aircraft have a thicker airfoil with higher thickness ratio, 16, 15, 17. Remember, this 17 means the thickness ratio, the thickness of the airfoil is 17% of the chord. When I say the roots, that's the airfoil at the fuselage connection, roughly. It's not quite, but roughly. When the wing meets the fuselage, it has an airfoil of 17% thickness. But at the tip of the wing, it has an airfoil of only 12% thickness. That means the thickness 12%, the chord of the tip. So there is a trend. It seems it would be wise to have a thicker airfoil near the fuselage than near the tip. And the reason for this is, why do you think they have made that decision? Why do they have a thicker airfoil at the roots than that of the tip? Why generally aircraft have thicker airfoils in the root than the tip? When I say root, I mean the inboard part of the wing, when it's attached to the fuselage. Why they are thicker? Yes, we have feedback due to shear. So Abdullah here is thinking structure. So in order to, because we have more shear on the cantilever, now I'm going to use the terminology of CE 203 if you have taken it. He's thinking the wing is just like a beam, a cantilever beam. It's fixed to the wall, which is the fuselage. So due to the high shear, I need a larger cross section. That's a good answer. That's a valid answer. However, structural guys are the last guys to consider when we talk design of aircraft. Typically, it's the aerodynamics, configuration, propulsion, and then the structures. So the thickness is determined not because of structures, but because of the volume that we need inside. Towards the root of the section, I need more room for the fuel tank. I need more room to retract the landing gear, if the landing gear will be retracted inside the wing. So we need more room. And of course, just like you answered, we need a stronger wing so it's thicker. But the main criteria here is the fuel tanks as well as the landing gear, because there are other ways to make the wing stronger without making it thicker. We can have more stiffeners inside and it will be stronger without making it thicker. So back to what we're doing. Again, we're trying to find CLmax. So we found that they use these types of airfoils. So if I choose an airfoil that's similar to this, then I'll probably be able to get its CLmax. So I'm getting the CLmax from the requirements from the category of the aircraft, not from one of the requirements that we have. So looking at these, it seems that they all or most of them use 5-digit airfoils. It seems that the thickness ratio at the tip about 12%, at the root 16, 15, 17. So here is my choice as a design team. We choose, that's a decision that you do, to have this airfoil at the tip, which is the same because it seems to be a popular airfoil. And this decision, this airfoil at the root, thicker airfoil, 18%. Maybe I have more range, so I think I might be slightly thicker than this. Maybe just to be different, and then I will check later. We will check later if it's going to be a good choice or not. So decisions are an important part of the design process. It's not like problem solving. It's not like you are given the problem and you expect to find everything. You will have to do some research, competitor analysis, you might call it. What are the other guys doing? In here, you will have to make choices that you can justify. So it's important when you make a decision like this in your design project. For example, you will probably not be using these two. Maybe you will use the same airfoil for the tip and the root, because you don't need much fuel in an aerobatic aircraft. And because you probably want maybe because you want to manufacture the wing easily. So it would be wise to have the same airfoil because it would be easier in manufacture. So regardless of your choice, almost all reasonable choice will make the airplane fly, but the designs are going to be better or worse if they are justifiable, if they have good reason, not just for that. Okay, that's a very important point. So in the example that we're having, these are the two airfoils. Before we start calculating CL for this, I will stop to see if you have any question in the rationale of picking the airfoil section up to this point. Okay. So if I look at these two airfoils, I realize that these are the CL alpha curve and this is the CM alpha. We don't care about the CM right now. Let's focus on the CL alpha. This airfoil at the root has a maximum CL of 1.8 this airfoil at the tip has a maximum CL of 1.6. But in my equation, I have only one maximum CL. So it would be only reasonable if I choose the average between the two values, and that would be my CL max of the airfoil. In order to distinguish between the airfoil and the wing, we write for the airfoil small CL max. So maximum CL of the airfoil is 1.7. Now that's for the airfoil. Now if this airfoil has a flap in here, this CL will increase by a value that we have found before in a table, I think table 5.1 or sorry 5.3. If you have your textbook, open your table 5.3, there is a table that will give me the increase in CL due to plain flap or slotted flap or whatever. So for a plain flap, for example, that increase is 0.9. So if the wing without a flap is 1.7, with the flap is 0.9, the total CL is 2.6. That would be a good value to use. I can go on and use this. However, this would be the maximum CL of the airfoil. The actual aircraft has a certain aspect ratio, so we expect the maximum CL to go down a little bit. Now, we have seen this before in chapter 2. Remember the A0 and A? The A that's calculated using the Prandtl lifting line theory, or that we had later on for compressible flow. We had A, like 3 equations for A. It tells you that it's not the A0, the slope of the CL alpha curve that we use. We have to change it a little bit. Rather than doing this calc, we can assume that CL of the wing will be slightly smaller than CL of the airfoil. Remember, CL of the airfoil is 2.6 that we had so far. So it's reasonable, very reasonable for finite wings that the wing will be roughly 0.9 of the CL max. Okay, so CL of the wing is about 90% of the airfoil CL max as a first approximation. We can check it later on, but as a reasonable approximation, I'm not going to use the 2.6. I'm using 90% of that, which is 2.34. And that answers my first question. What is CL max of this aircraft? You see, there isn't rocket science in here, because I'm not calculating accurately the CL. I am estimating a good value for CL that will help me estimate other parameters like the weight, the wing loading, thrust weight ratio, draw the aircraft, and when I'm done, I will check that value. Okay. Any question in the estimation of CL max? So I always like to call it this. It's estimation, it's not calculation. So in a quiz, for example, if I give you a design problem, I ask you find CL max, you shouldn't come back to me and say, well, you didn't give me the airfoil. Well, you pick one. You didn't give me the aspect ratio. Assume one reasonably if you cannot calculate it. Okay. You didn't specify the type of flap. Well, you specify it and calculate based on your specification. So it's not always that you will find all the information of the equations there. So starting from chapter 8 in your course AE 240 until you finish AE 247, get used to the sentence that says assume reasonably any missing data, because this is what we do in design. We assume reasonably. Any questions up to this point?
ايوه دكتور طبعا في يعني if we're going to assume في guidelines نمشي عليها صح؟
Not guidelines, reasonably. It's the word reasonably. You see, when I said here, when I say what was the objective 20 minutes ago, find CL max, right? An unusual, unreasonable assumption would be, okay, I will assume CL max is 2.5. Why? Because I cannot justify it. I cannot tell you why it's 2.5. So that's not a reasonable assumption. It's not based on knowledge, right? Or I can say, okay, CLmax is, well, I need a better design. I will make it 4. I will make it 4. Okay. Now, how can I get 4? Do we have an airfoil that has a CLmax 4? No. Do I have an airfoil with a flap that has a CLmax 4? No. Why 4? Why? So what we assumed are pieces of the puzzle until we get a reasonable final answer. So we assumed an airfoil type, which is okay, as justified by other aircrafts. We took an average, which is a reasonable way to do this. We assumed an increase in CLmax of 0.9 because of a plane flap, which we have evidence that shows us that it is 0.9. I'm talking about the guidelines you are asking for. We add them. I am reducing CLmax of the airfoil by about 10% to account for the 3D effect. We have something on our hand that justifies this until I get the final answer. Does this answer your question?
Yes.
Okay. And we will do this over and over. You will do this in your team, and we will continue to do this starting from this point forward. Because we are not solving problem, we are designing something that's not there. Okay. So we answered the first question, what's CLmax? Then comes the second question. What would be the wing loading? So I need to go back and look at my requirements. What drives the wing loading? And I will go one by one. What is the requirements? In here. Is the maximum level speed affected by the wing loading? So I have to go back and check my maximum level speed equation. Does it have W over S? And I will find it has W over S, but it will also have T over W over in there. But since I don't know the thrust, that's not going to be a good choice. If I go to the range equation, Breguet equation, you will, do we have wing loading in there? Do we have W over S in the range equation? Anyone? Do you remember the range equation? R equal?
And
Do you have
all
what,
that.
Victor?
The range.
Yes, you said we have something in the range.
Oh, do we have wing loading? The objective is the wing loading. W over S. Do we have W over S on
Yes,
range?
I think, yes, I'm pretty sure.
No, we don't.
And
The range
those.
equation has the specific fuel consumption because any equation will have the parameters that affect that performance. What affects the range? Specific fuel consumption, of course. C, the speed, V, L over D, how aerodynamically clean the aircraft is. So L over D is there because this affects the range. And how much fuel you can carry, W minus W or W over W. But the wing area is not there. It's not in the range equation. If you increase the area of the wing, the airplane will not go any further. It's just like if you increase the size of the doors of your car, the car is not going to go any further. Or if you increase the size of the passenger cabin or the seat, they have no effect. Wing area is not a factor in the range. So the wing loading is not a factor there. What about the ceiling? How high the aircraft will go? Well, yes, it has a wing loading in it. It has W over S. The bigger the wing, the higher the aircraft can go. But it also has the thrusts, and that's a problem because we don't know thrust. So I will skip this one. Rate of climb definitely has thrust in it, and wing area and wing loading. But again, you see thrusts appear in many equations that has wing loading. But when we get to the stall speeds, you will find that we have the weight, we have the area, we have CLmax, and we have stall speed. We don't have thrust. That's a good equation. Let's use this to get the wing loading. So I will use the stall speed. The same goes for the landing distance. If you look at the equations of landing distance, you will not see thrust. You will see only W over S, in addition to other small parameters, K, CD naught, and so on. So my point is we will determine the wing loading from the stalling speed and the landing distance for this aircraft. So I will start by calculating the wing loading that's necessary to satisfy the stall velocity requirement. The problem says the stall velocity is 70 miles per hour. 70 miles per hour means 102 feet per second. So I will go through my textbook, go back in chapter 5 and find the equation of the stall speed. Actually, I don't have to do that. It's a very simple equation to derive, right? Lift is equal to the weight equal 1/2 rho v square S and CL max, and substitute with whatever values you have. So we have the stall speed in here. We have CL max. We have just found CL max to be 2.34. Stalling typically is required to occur at sea level when the aircraft is landing. So I will put sea level density. So the only unknown in the stall speed equation after moving everything to the other side is the wing loading. You will realize that the design equation chapter 8 are exactly the same as the performance equation of chapter 5, except that we move everything to the other side and keep only one parameter. Just like what you did in the quiz. What in your quiz, I asked you to determine the wing area or the thrust, maybe. One section was the wing area, the other was the thrust. So that you move everything to the other side and determine maybe the wing area or the thrust. So in here, CL max is known, stall speed is known, density is known, the only unknown is the wing loading, gives me a wing loading of 29 pounds per foot square. That means if you want the stall speed to be 102 feet per second, which is 70 miles per hour, your wing loading should be 29 and your wing area is the weight divided by the wing line. If you want S, it will be W over the 29. It will be the 5,100 that we had last time divided by 29. Okay. Any questions? Okay. So we calculated the wing loading. Why bother and go for the landing as well? We now know the wing loading and we have the wing area. Why do we care about the landing? Why will I go and calculate again the wing loading from the landing? Because I have two requirements. The aircraft must satisfy this stall speed and must satisfy a certain landing distance. The landing distance was 2,200 feet. There is no guarantee that this wing loading that I got from stall will satisfy the landing distance of 2,200 feet. So I must check that. Okay, so I will go to the landing and I will use exactly the same couple of slides we had in the landing in order to determine what would be the wing loading and the wing area that will satisfy the landing condition of 2,200 feet. So the unknown in the landing performance now is not what is the landing distance as you did in the homework. The homework was what was the landing distance? No, the question is if the landing distance is 2,200, what should be the wing loading or the area of the wing? They mean the same thing. So I will go through the landing performance and I hope you still remember the landing performance. But before I do this, I'll stop to see if you have a question. Okay. So the question that we need to answer now is if this distance is 2,200 from when the aircraft is at 50 feet high and it's specified in the requirement, it should be at 50 feet until it comes to a complete stop. If this total distance is 2,200, what is the wing loading of the aircraft? Or what's the wing area of the aircraft? So just exactly, we will repeat what we did in the landing. Except that in this case, we will know the left-hand side and there is something in the right-hand side that we don't know. May I remind you that in landing we had the A area when the A length when the aircraft was airborne, we call this SA. Then, in order to calculate SA, we had to find the flare height in which the nose will come up and the aircraft will rotate, touchdown, roll for 3 seconds, N is equal 3 seconds, before the pilot hits the brakes and comes to a complete stop. The sum of the 4 distances here should be 2,200. The first distance and the second distance, we had them exactly known numbers. They don't depend on the wing loading. Only the last 2 will depend on the wing loading. So let's calculate them one by one. I'm just repeating exactly the same 2 slides. You will probably have seen exactly these slides back then. So the starting point for landing would be what is the flare speed? The aircraft will slow down until at a certain flare speed it will start to rotate. So the flare speed is 1.23. We have that from operational constraints on the aircraft. That's nothing new. So since I know Vstall, I know the VF. If I know the VF, I know the radius. So have equation that gives me the radius. I'm using the equations that we had in chapter 6. I'm just repeating them. So I know the radius. I know the angle that we have is 3 degrees for transport aircraft, and this is a transport aircraft. If it was a military aircraft or a small home-built aircraft, it might be 6 degrees, but it's 3 degrees for transport aircraft. And I know R, so I know the flare height, and I know the distance when the aircraft airborne. Nothing here has to do with the wing area or the wing loading. Everything here depends on the stall speed as well as the approach angle of 3 degrees. Okay. So if I know this SA turns out to be 900 feet, I will calculate the flare distance R sine theta 130 feet. Again, I'm just using the equation. One smart way to do this for your team, rather than flipping through chapter 5 and 6 looking for the equation, is to look at the summary of the equations at the end of the chapter. It will give you exactly what you need. You can highlight these equations. So this distance is 889 feet. This distance turns out to be 130 feet. May I remind you that when we added them in the examples in chapter 6, they were slightly higher than 1,000 feet. You see here, they're about 1,020, slightly higher also than 1,000 feet. So if this distance from here to here is 889 plus 130, then the remaining 2 distances should be the difference. So the remaining 2 distances is 2,200 minus 889 minus 130, giving me 1,100. So the sum of the distances when the aircraft is on the ground is 1,100. Do we have an equation for the 2 distances when the aircraft is on the ground? Yes, it is the SG equation. It has a term for the first part and a term for the second part. The first part when there are no brakes, the second part when there are brakes. Again, it's an equation from chapter 6. And now that I know SG to be 1,100, SG is the difference between the 2,200 and the 80, 89 and the 130. So it's that distance, SG. So I know SG. Now let's see what do we know in here. N is the number of seconds the aircraft will roll without brakes, typically 3. Mu is the coefficient of friction with typical runways, 0.4. No one is giving that. It's typical in the industry, so it will not be provided in a problem. You will have to assume them. Okay. Now, remember, this is a conceptual design. When we get to detailed design, maybe this 0.4 after we do experiments or the company will make experiments will turn out to be 0.38. So that will be revised then. But in conceptual designs where we don't have experiments, we're still generating the aircraft, I can use the 0.4. J is 1.15 in the equation. If you remember, this was how fast the aircraft is, 1.15 times VSTOL. So density is sea level, CL max, we have it. The only unknown in here is W over S. Okay. So I'm putting the numbers now. JN density, coefficient of friction, SG, 1180. The only unknown is W over S. Unfortunately, it appears here as a root square and here as a W over S. So you can get it from your programmable calculator, or you can say this is just like a quadratic equation where my X unknown and this is X square term. So I can solve a quadratic equation in order to get the W over S. Of course, you will get two roots for the quadratic equation. Please ignore the one that's unreasonable. Maybe I will get W over S negative. That's an unreasonable value. Maybe I can get W over S of extremely low number, like 3, which doesn't make any sense. Okay, so you will get two values. One of them will be definitely unreasonable, and the other one would be the wing loading that's required to satisfy the takeoff distance. Any questions?
Yes, Doctor.
Yes.
When we say that,
Mohammed.
When we say that the aircraft will land on a grass, what will change in this equation?
Okay. If the aircraft lands on a grass, what do you think? Do you think the first part will be affected?
No.
No, not the first and not the second, then and not this one because it's rolling. It's that one. So the coefficient of friction will probably not be 0.4. Probably will be less, slightly less, maybe. So we can assume 0.35, 0.36, maybe, and we will use that. So that will be the effect that we have on the grass. It will not be a major effect. It will have some effect, but it will not be a major effect. The effects of the grass, I know you are referring to your design project. Why grass is there? It will come in the design of the landing gear. Landing gears pushing on the soil cannot push with certain pressure if the soil is soft. So when we come to the design of the landing gear of this aircraft, we will deal with the grass. It will have more effect in there. It has some effect here, but the major effects of the runway type will be on the landing gear. So we will have to pick slightly larger landing gear than if the aircraft was landing on regular paved runways. Okay, does this answer your question?
Yes.
Okay.
But with the parameter n.
N is the number of seconds for which the air. Well, it will, but think of it this way. In this aircraft that we are having, we are designing an aircraft that will carry 5 passengers, 1 pilot, so 6 passengers. How many of these aircraft you have seen landing on grass? It's not a requirement in this design. It's a requirement in your aircraft, I think, right?
Yes.
Because it was an aerobatic aircraft. So not in the one that we are dealing with right now, but in your design project. N is typically 3. Probably the pilot was not the brakes once he touched down. If you want to put it 2, that's fine. By the way, reducing N will mean a shorter runway. Because when you reduce N, you are reduce the rolling time on the ground. That means the aircraft will come to stop faster. But 3 is typical for larger aircraft. Remember, in one piloted aircraft where you have or one passenger aircraft or 2 passengers, the pilot can do anything. He can just hit the brakes once he touched down. It's sort of close to home built aircraft. So there are no like strict guidelines for the operation of the aircraft. You can put it 2 if you want. Okay.
Okay, thank you.
Okay, now comes the tough question. And we are going to conclude with this question. I have wing loading here 41.5. That means the wing area is W over 41. But in the stall, we have another wing loading 29. That means the wing area is W over 29. Obviously, I cannot have two values of wing loading, otherwise I will have two wings. One that's suitable for the stall and one that's suitable for the landing. The question is, choose. I have to pick one, or should I take the average? What should I do? I have two values of the wing loading, and at the end of the day, I have to pick one. Should I pick one of them? Should I take the average or what?
Can I change the requirement? Maybe.
I can change the requirement. Can you? If I can tell you, design me a house that has 3 rooms, you tell me, well, I have a trouble, I'll make it only 2. We don't mess with the requirements. Because if you change the requirements, you will not get the design done the proper way. I can do whatever I want and then I say I change the requirements. Nope, you cannot change the requirements. Any other question?
Depends on the calculation, right?
Depending on what?
If they're both reasonable, we take the average. If one of them is like negative or really small, we take the other one.
Okay. We take the other one, you mean the higher?
The more reasonable one.
What is reasonable? What's more reasonable out of the 41 and 29? Which one is more reasonable? 41 or 29? What does reasonable mean?
Depends on the requirements you give me.
Oh, well, you have the requirements now. We are members of the same team now. You have the requirements as I have it, and you are telling me we will pick the more reasonable one. I'm asking you, what's more reasonable, 41 or 29?
Oh, you have to take I think the average is the more reasonable.
Okay, so the average. Keep both in mind and later on decide which suit us better as we move along the process. Now, here is the example that I'd like to, let me give you an analogy of this. Okay, and I give the same analogy for the other team to help you understand that you have to choose at some point to satisfy the requirements. I was telling them I am overweight, and when I go to a cardiologist, he tell me if you want to keep your heart safe, you have to bring your weight down to 90. But I have problems in my knees. When I visit the doctor, the other doctor, he tells me you are overweight. You need to reduce your weight to 80. So here's one telling me you have to be below 90. The other one tells me you have to be below 80. Now, what's more reasonable from your point of view? Which one should I pick? Or should I take the average and say, okay, I will be 85? Well, it has to be the 80. So in order, whenever you have two requirements, pick the one that satisfies both. So in this case, I will have to go to the lower one, 80, to keep my heart and knees safe. It's exactly the same here. The stall requirement says the 29 means if you want to have a wing that will give you this stall speed, this wing has to have a wing loading is equal to 29 or less, because the more wing area, the lower is the wing loading. You see the wing loading here? This one, the 41, will give me a wing area of W over 41, but the other one will give me a wing area of W over 29. Which one will have the biggest wing? The one coming from the 29 or the 41?
From the 29.
The 29. It is the one that's more safe. It's the one that's reasonable, if you want to say it. It's the 80 kilograms that I have in my case. So if we have several values of wing loading, we always pick the lowest value because it means the biggest wing. Not because it's reasonable, not because it's average, because it is the value that will satisfy both. You see, this 29 will give me this stall velocity and will give me a landing distance that's 2200 or less. It will give me less than the 2200. Is this clear? But if you pick the 41, yes, you will satisfy the landing distance of 2200, but the stall speed will not be what we had before. You will violate that requirement. So we never take the average, we take the lowest one. So the lowest is 29.3. We will take this and we will use it, and it will give me the wing area is W. We have W from last time, we calculated it last time. So the wing area of this aircraft is 176 feet square. It will satisfy both the requirement of the landing as well as the stall. Is this clear? Next time, inshallah, we're going to use the remaining requirements, other requirements, maybe climb, maybe ceiling, whatever, to determine the thrust-weight ratio and hence the thrust of the engine. And then we will start to put the engine inside the fuselage and so on. Yes, there was a question. Question? Okay. So thank you, everyone. We are done for today. You can check the